So that last video cut off a little abruptly, and honestly, I had to start with a new set of guided notes because I can't find where I left that other packet. But what we'd been talking about is solving sort of a system here and thinking about how can I mash up these two equations. So I want to find values of a and b that make this true. So it's true for the 54 and the 3. So 3 comma 54, I replace x in the base equation for an exponential function with 3. I replace y with 54, and then I do it again, replacing x with 1 and y with 6 in this equation. So if I want these to eliminate, like typically using, if we were eliminating like in a linear equation or a quadratic, we'd have our terms added or subtracted. So we could typically add our columns or subtract our columns, but here these two are multiplied. So the only way to sort of like get rid of either the a's or the b's is to divide. So there's this cool thing I can do where I can just divide the two equations. So I intentionally wrote the higher exponent on top to make this clean up a little bit nicer. So 54 divided by 6 is 9. A divided by a is 1. And 3 squared b cubed divided by b is b squared. So in other words, I'm looking for a value where b squared is 9. So b must be 3. Okay, and if I plug that back into either one of these equations, for example here, 6 equals a times 3, then a must be 2. And that allows me to sort of think about this equation as being y equals 2 times 3 to the x. And I'll show you a slightly different way to do it on your example number 2 as well. So a different way that you could sort of explore this relationship is you could make a table, sort of like what we had on the other page. You could think about 0, 1, 2, 3, and fill in what we have. So we know this guy's exponential. We know that's our base function. So we know when x is 1, y is 10. When x is 3, y is 40. So we want to think about something gets multiplied as we go from left to right as x goes up by 1. So like, what do I multiply by 10 to 10 to get 40 is times 4. So I have to it's not like I'm cutting this in half. I'm not dividing by 2. I'm taking its square root. So in other words, times 2 and times 2 again gives me times 4. So it's kind of almost helpful to picture what that middle number is. So if it's times 2, that's a 20. So 10 times 2 is 20, 20 times 2 is 40, and I can actually work this backwards to realize that a 5 would have been here. 5 times 2 is 10, times 2 20, times 2 40. This is good because this times 2 ends up being my b value, and this 5 is my initial value, my y-intercept. So my function is going to look like y equals 5 times 2 to the power of x. And I can replace both of these values in that function, and I'll get a true statement. So in other words, 2 to the first power is 2 times 5 is 10. And 2 to the third power is 8 times 5 is 40. So both of them check out. For example number 3, this says a store sells trampolines, and the table shows the numbers y of trampolines sold during the first 7 years the store has been open. Write a function that models the data. So before I kind of try to break this down, I'm just looking at, like, in the first year the store was open, they only sold 12 trampolines, and every year that number goes up by a little bit and a little bit and a little bit, so that by the end of 7 years they've sold 96 trampolines. In that 7th year, not like at the end of 7 years, but in that year they sold 96 trampolines. So if I'm using this graph, I really want to maximize the space I'm given. So I want to say there's 21 spaces here and maybe 28 or so here, 30 here. So I have 7x values. So I'm going to just kind of treat this guy here like the origin. So this point is 0, 0. And I'm going to make every 4 spaces a 1, and that's just to kind of spread out the graph so it's not compressed in this little teeny tiny area. To figure out what I should count by on this axis, I need to get from 12, but really it'd be nice to start with 0, up to 96. So it's close to 100. So I'm going to count by 5s because I have just over 20 spaces. I don't need to label everyone. I might decide to say, let's see, 5, 10, 15, 20. 25, 30, 35, 40, and I can do this all the way up. I also want to label my axes with units, or sort of words. So I went ahead and finished numbering here and labeling my axes, and now I'm going to plot my points. So 112, it makes sense that that should be just more than 10, that I don't have a 0 value because you can't sell any trampolines at the end of year 0, right? 216, and again, this is going to be a scatter plot because there are no points between these values. 325, 436, and I'm going to just quickly go through and plot the rest of these. So I just went in and I finished filling in these values, and you can see that that approximates a pretty nice exponential curve. Now, in real life, our numbers are messy and we don't tend to have the exact same amount of growth over time, but if you look at these numbers, it looks pretty consistent here in terms of an exponential model. So I'm going to go back to these values, and one of the best things we can do is if we want something to fit this data, you can find the rate between these, so the constant ratio. So in other words, what do I multiply to 12 to get 16? And I would get that by taking 16 and dividing it by 12. And that would be, let's see, 4/3. So that's times 1 1/3 repeating. And I could do this all the way down. But then I'm going to get all these different numbers and I'd have to average them. So add them up, divide by the number of them. Another thing I can do is I can count these spaces, 1, 2, 3, 4, 5, 6. And what I can do is I can find this ratio here, 96 over 12. And I can sort of imagine the b value, whatever this is, that I multiplied here, it happened 6 times. So b to the 6th is going to equal the ratio of, what did I multiply to 12 to get 96? Okay. So if I do this, if I put this in my calculator and I take the 6th root, I'm going to get b is about, and again, I can do that pretty easily by just doing 96 divided by 12 raised to the power of 1 divided by 6, and that'll spit out a b value for me. And I want to say it's something like 1.41. So that's my growth. That represents, by the way, 41% growth per year. Okay, the 1 is sort of like, it's on top of the value, whatever the previous year is. Now, something else I want to do is I want to kind of back this up and imagine, okay, so in order to find the a value, I want to back this up to year 0. And year 0 is going to be whatever I had to multiply to, again, that 1.41 growth factor to get 12. So if I do 12 divided by 1.41, I get about 8.5. So that gives me my initial value, which doesn't make sense in the context of the problem, but which we need in order to write the function. So to write the function, I'm going to use this base function here. Y is the number of trampolines sold at the end of a given year. A is the initial value of 8.5. B is the growth factor of 1.41, and that's going to be to the power of x. So that is my function.